Hello, my name is Nikolay Lyfenko. I work at Positive Technologies as a machine learning engineer. I'm interested in information security and machine learning. I think that many information security problems can be solved through the help of machine learning. Today at Data Fest, I'm going to speak about web bot detection and classification. What are web bots? How can they be detected in real time using Elasticsearch, Kibana, Stash, and shallow machine learning? First of all, we need to define what is a web bot. Many researchers have many definitions, but most common is that web bots is a software generating automatic activity regardless of usage. Here you can see definitions from Imperva, Cloudflare, and some researchers. You know that web bots are everywhere, and approximately half of web traffic is generated automatically, and more than 60% of web bot traffic is malicious, according to Imperva research. There are not only bad bots, but there are also good bots. Well known that there are crawlers, RSS readers, but there are also malicious bots such as spammers, which can be used for ranking fraud. There are scrapers. There are also vulnerability scanners such as Aconetics, Pursuit, and others. There are Trojans that can be used for credit card fraud. Bots are not the same. They can be different in their sophistication level. There can be a simple one that can perform simple requests, simple scripts. They don't masquerade. There are also moderate bots. They are more complex. They use headless browsers, and even they can execute JavaScript. And there are more sophisticated ones. They can mimic human behavior. Here you can see philosophical quote from book Machine Learning and Security. The main idea of which is that if you solve your bot problem, you make bots more sophisticated. So it isn't enough to block or somehow mitigate bots. You need to analyze them more and more. Why do we need bot detection mechanism? Of course, you can decrease your server load by 10%. You can understand traffic deeper. You can't improve your site because there is a lot of noise. You can't perform any A/B testing. You can be the aim of inventory exhaustion attack. It is a type of attack where some automatic scripts put a lot of stuff in a cart at your e-commerce site and then don't buy anything. And this approach can be flexible. You can add new bot classes and update on the classification model. Now I'm going to speak about proposed approach, but I need to define some stuff. First of all, object of our research is HTTP session. Session is a sequence of requests from one host, and host is defined by a unique IP address and a user agent. We're going to use machine learning to predict those sessions with the help of some statistical features, which I'll tell at the next slides. We're going to solve two tasks. First, we need to define bot. It's a binary classification task. We're going to separate bot traffic and human one. And then if this traffic is predicted as a bot traffic, we need to classify these bots into several classes. But as we are solving supervised classification task, we need session labeling, those request labeling. Naive approach is to use user agent analysis, so-called mapping from user agent to predefined class. Then we can extrapolate this approach with the means of keyword analysis. For instance, if spider is in some part of HTTP header, for instance, in user agent, then perhaps it can be some kind of automatic thread. And we can try to use thread intelligence by means of IP reputation. I need to know that we don't use user agent header for model training. We use it only for data labeling, and model training is used only with the behalf of statistical features. Here you can see the picture of training pipeline. I'm going to describe it a little bit. We use packetbit for data parsing, where we store our events at logstash. Here we create a unique ID for session. We concatenate hash of real IP address and user agent, and associate this IP address with a task which is created and stored at RabbitMQ, where a number of workers can be connected to it and solve two types of tasks. First task is to label session with the help of browse-cap, for instance. And the second worker can process session, create feature matrix, and store it at Redis. Those matrices and labels are stored at Redis, where periodic task from data saver can take all this data and store it at Elasticsearch, aggregate it there, and then periodic learner task can go to Elasticsearch, take all the data, perform model training and cross-validation, and as artifact of it, we create a trained model. Prediction evaluation for this model done as follows. We take unlabeled data from Redis, put it through our predictor, which uses trained model, and store results at Elasticsearch, where user can analyze these results with the help of Kibana. It's a graphical user interface for Elasticsearch. Here you can see some features that are used for creation of session features. For instance, number of requests per session, number of headers, and etc. We use random forest and this scikit-learn version for model training. This approach wasn't always, as I said. There was some evaluation here. We moved from Scapy packet processing to Elastic Logstash Kibana stack because there was a lot of packet loss there. We moved from UJA labeling to browse-cap and expert labeling because there wasn't enough data at UJA. And task was redefined from three-class classification to two separate tasks. First we detect bots and then we classify them. Now I'm going to show some experiment results. We analyzed our approach using Security Lab data, which has more than 15 gigabytes of traffic. There are more than 2,000 bot sessions and more than 8,000 human sessions. I'll show some results for online and offline tasks. Here you can see offline data, offline results were performed with the help of stratified scaffold cross-validation. Here you can see that we can separate bots and humans pretty well. If we classify those bots, we can see that not all the classes have the same results. For instance, we predict RSS reader class pretty well, and we have more than 108,000 examples there. But some classes, for instance, lib tools, doesn't perform well. There are raw errors there. Here you can see measure results from line classification, and here you can see precision and recall for those examples. I'm going to speak only about two of them. They are more interesting ones. For crawler class, you can see increase in performance during the time for precision, recall, and of course of measure. But for RSS reader class, there are no increase. There isn't any increase. They are stable. Here you can see example for impersonator bot. It performs several HTTP requests. They are common. They're even similar. But user agent here is valid user agent used by humans. And if you use here a simple approach that maps user agent to some category, you would fail, because this user agent is used by humans, and here we have an impersonator. This bot tries to mask its activity, but we define it as an RSS reader because model can generalize its behavior. Here you can see bot features from Kibana table. You can see headers counts, len of packages, len of pages, etc. Here there are bot requests. For instance, Uptime Robot performs separate requests to get main page. Here are some human features, and human requests and those features are calculated from these requests. We have here some challenges. We analyze sessions only with the number of requests more than 10, because we use statistical features and we can't create model when we haven't got any data. Perhaps thread intelligence could help us here. We have a true labeling problem. That's why we can't properly evaluate model. This true labeling problem is defined as follows. Here at the picture you can see TSNE session visualization for human and bot data. Blue dots are bot sessions, and the red dots are human sessions. And at some areas there is a great mix. So perhaps there are a lot of errors in labeling. How can we relabel that data? We can simply perform some kind of fit predict and then correct false positives manually. And this expert labeling makes our metrics higher. We get precision and recall increase. Another challenge is that for some data, as I said, we don't have enough. For some classes, we don't have enough data, and it's very bad. We don't know when to stop predicting, because data is accumulating, and perhaps we can stop predicting after a sequence of strong confident predictions for that session. Here I'm going to show you some results and key findings of this research. We have precision and recall for detection more than 95%. For some classification classes more than 80%. Can we do better? Yes, of course. For instance, we can add some more features. Adding robots.txt feature increases our total F measure by 3%. And as I said, correct true labeling increases of measure by 4% for class both. What can be done next? We can use TI, and we can add more features. For instance, entropy of paths, pages, whatever. If you're interested in this topic, you can read more about this at these articles. Thank you very much. I'm ready to answer your questions.